Welcome to my second class on SLR shift parsing. The prerequisite here is that you have to know about how to construct the set of states given a SLR zero grammar. So, if you look at my previous slide, you find out that for this particular grammar, I have created the set of all states like this, and this has been elaborately stated in the last lecture that I had. So we'll assume that we understand the construction of this sets of states and go ahead with this. What will we do with this is we would like to find out or construct a method by means of an example in which we'll show that the basic technique of parsing now becomes mechanical. I mean, if this particular, this particular state machine, you can see that these are all state machine. These are all states, and this is a big state machine. In fact, this is a deterministic finite automata or a DFA. So given this DFA and an input string and a stack, how can we construct a method so that parsing becomes fairly easy? And we'll do that through an example so that we can develop an algorithm after that. The key idea of designing algorithm is to understand the methodology through different types of examples, and only after that you can reach to a particular kind of a solution which you can realize as an algorithm. So let us go step by step, very quietly, very slowly, so that we understand the method well, and the method becomes intuitive to us. Method becomes almost natural to all of us. So let me go to the next slide. Uh, in all these slides, you will find out that the grammar will be written in the at the very beginning, and at the left we will find out the relevant states from the original state diagram, and I have assumed that we are using an input stack. At the bottom of the stack is initialized by a dollar and a zero. The stack has to be read from left to right. I mean, the rightmost end is the top and the leftmost end is the bottom. So at the very beginning, we are saying that the stack contains dollar and a zero. Zero means the state zero, and state I0 or state 0. And the input is a very simple input, a sentence AAB. Like dollar is the bottommost element of the stack, similarly dollar becomes a delimiter of the sentence. I mean, after the sentence, a dollar is put to understand that we have come to the end of the sentence. So we start in state 0, and when we find that the input symbol is A and the state on the stack is 0, then I find out from the state machine which we constructed that if I am in state I0 and I have an input symbol small a, then where should I go? It says that you should go to I5, and that means it says, and then it says that you put this dot across this a small a, which means that you shift this input symbol to the stack. So already the stack contains 0. Now the symbol the stack contains a, and it says that go to the state 5y, because from the state I0 using the symbol small a you go to state I5. So therefore it says that push the input symbol into the stack, right, and then push the state onto which you are going into the stack. So what is the current state that you are in right now? Right now you are in the current state which is known as 5, right, because 5 is at the very top. Now once I see 5 at the top and a just beneath it, I understand from this particular state, I understand that I cannot go anywhere to find out the longest viable prefix. So what is the only option that I can do? I can try with reducing. I mean, I try with replacing the right hand side with the corresponding left hand side. So exactly that is what we will try to do. Exactly that is what we'll try to do. So you see that we said that reduce using this rule. So where from did I get this rule? Only from the state 5. So since the current state is 5, I look at 5 and I find out what this state says to me. This state says that the longest viable prefix has been achieved. Why? Because the dot is at the end and no other item is there in which dot precedes any symbol. So therefore, only option here is to actually reduce, means reduction means replacing the right hand side using the left hand side of the rule, and which rule that will be guided by the state that we are looking at. So therefore what we do is we I pop two symbols. So I there is only one symbol to the right hand side, and I know that I am always pushing in pairs. But what I mean by that, I push the input symbol as well as I push the state into which I am in. So if I have to pop the number of symbols that is in the right hand side, then I have to pop twice of that. So I popped twice, I got 5 and a out. So what is remaining there? 0 remains, and then this capital A is pushed again. So a reduction means I have to pop and then I have to push. What I have to pop? I have to pop two n symbols if n symbols are at the right hand side of the relevant rule. And what I need to push? I need to push the left hand side of the rule, right? Now the next question is, now my stack top is, if my stack top is capital A, that is not the norm. Norm is my stack top should be a state number, not a non-terminal or a terminal. So therefore, what does it indicate? It indicates that actually what is your state, current state is determined by you go to state 0 and then find out where capital A takes you. So that's what we did in the next slide, and we can see that. See, this slide says if you are in state 0 and if you get a capital A, you go to state 1. So I say go to 1, that is number. So that is basically 0A, 1 is my stack from the bottom. 0A, 1, capital A, 1. So while shifting into the stack, shifting an input symbol to the stack involves just one push and then one more push to push the current state into the stack. So only two pushes are required for completing a shift operation, but reduction operation includes number one, popping out from the stack requisite number of symbols. In fact, if the right hand side contains 3 symbols, pop out 6 symbols, and then after you pop that out, push the non-terminal to the left of the rule that you used to reduce, push that in. So so a number of pops, one push, and then one more push, so that your current state can be correctly positioned at the top of the stack. So while your input is not consumed, lots of activities inside the stack. Also, a very interesting thing is, see, what is the sentential form AAB? What is the sentential form AAB? What is the sentential form AAB? What is the sentential form capital A, small b? So the sentential form that you have at any point of time is a combination of the stack content from the bottom and the input symbols which are remaining from left to right. So at any point of time, if you are interested, if you are curious to know what is the current sentential form, you have to write down the grammar symbols from the stack from bottom to top, concatenate that with the input symbols that are remaining, and the underlined input symbol is the one which is the current input symbol. What is the current state of your entire parsing algorithm? The current state is at the stack top. And what is the current input symbol? That is at the very left of the input string that are remaining. I think I am very clear about what I said. So let me go to the next slide for your next operations. So now my current input state was 1. My input symbol was A. So I look at current state I1 and I see where I go using small a from I1. I see that I go to 7. I go to I7 that will be my current state, and therefore it says that you actually shift that the moment you have an arrow from I1 to I7 using a small a. That means whenever not terminal symbols are used for a transition from one state to another, it basically tells me that you have to shift that input symbol into the stack, and the current state will be the destination or the target state as given in the state machine. So I shift small a and I go to 7. Very simple. I shift small a. Why? Because from I1, this I1 was my current state. Using small a, I go to I7. So there is an arrow. So I shift small a, and then my current state is no longer 1. My current state becomes A. Now next slide. Next slide you see that it says that I have reached the handle. I have reached the end of the variable prefix. And however, this is not the end of the sentential form. The sentential form as of now, as in this place, is now capital A, small b. Now I see that capital A, small a appears here, and this state 7, number 7 state does not tell me to advance, it tells me to reduce, because this dot appears at the very right end. So I reduce using this capital A, and as I said, reduction means a few steps. What? Pop out number of symbols. How many symbols are here to the right hand side? 2. So how many symbols do I need to pop? 4. So 1, 2, 3, 4. So up only 0 remains. Then I push. What I push? I push the left hand side. So this, and then I again push here A. Do not assume that I popped only 3 symbols. No, I popped 4 symbols, and then I inserted this capital A. And now what is my current state? Again, what is my previous state? 0. So I have to go to state I0, and then I have to find out where I should go using this capital. So you see, from 0 using capital A I can go to 1. So I say that go to 1, and this is 0 capital A 1. There is a small mistake. This will be 7, not 5. In many slides coming forward, this small mistake 5 may remain there. So please be aware of that. Next, I go to so what is there? I have 1 at the stack top, and I have an input symbol B. So if I have any transition from the state I1 using the input symbol B, then I know that I can shift small b into the stack and go to the next state wherever from 1 small b takes me. So let me see what it is. Yes, so I see that from I1 using B, I can go to different states. I can go to I can go to a state called I2. So I push B in, I go to the state 2, and that's it. So now only dollar remains. My input symbol as such is not there, but the sentential form however remains, and the sentential form right now is capital A small b. That's it. So now let me go to next one. See, of course, you see this dot appears at the end in this particular item, but there are many places where this dot actually precedes some symbols. So that means this dot tells me you can go further, and this dot tells me you can stop, and because you have found out a handle. Now this is a dilemma. Which one should I do? And this dilemma can be resolved by one. For example, what I am seeing at the input, I am seeing at the input dollar, and what can I see at the input from I2? I can see at the input only small a. So small a is not there, dollar is there. So let me take a chance by reducing this small b to b and find out if I can proceed further. This could be one solution, but that solution is kind of trial and error. So we'll find out later on that we have a better mechanism to find out whether we should go ahead with shifting, or we should declare an error, or we should uh, try with reduction. So an affirmative and very decisive answer to this question can be given and that will be given at a later part of our lecture, maybe next day, maybe next lecture we can talk about that. But for the time being, I understand that this dot says reduce, these dots say actually shift. So this is called this famous shift reduce conflict. and we'll have some mechanism to resolve that crisis. For the time being, I'm resolving this crisis like this, that since the input symbol does not have anything which I can use to shift, and therefore I'm going for a reduction. So I go for a reduction. Which rule? This rule. So I reduce how many symbols to the right hand side? One symbol. So how many to pop? Two symbols. So I popped two symbols. And now what is the current state? The current state is 1. What is the input symbol? What is the symbol to be pushed into the stack? Capital B. Why? Because in this item that I used for reduction, the left hand side is a capital B. Now at this point of time, as I said, I cannot have the stack top a terminal symbol or a non-terminal symbol. I always have to have at the stack top some state number. Which state number do I need now? I need to find out using one and as the current state and capital B as the symbol. Where can I reach? So let us go to the next slide to see that particular thing. So yes, I mean, to our pleasure, I noticed that from the state I1 using capital B, I can go somewhere. You may ask me, had this not been the case, what should I do? I should declare an error. So that if I assume that from state I1 using the capital B symbol, there is no transition in my state diagram, then what should I do? If that is your question, the answer is pretty simple. If that is the question, then the answer is there must be something wrong in your sentence, and the sentence cannot be parsed correctly. So that says that it is an error state and you cannot proceed further. But that is not our case now. So what we know now is from 1 using capital B, I can reach the state I3. So I say that my current state now is becoming 3. So I have the current state 3 and I have the input dollar. See, that is why I inputted dollar. At the end of the string, there will be nothing, but nothing. I mean, even if you were writing a C program, you know that a string has to end with an backslash 0 symbol, right? Right. So a string has to have a delimiter, and this delimiter is basically this dollar here. So what to do now is I know that there is no input symbol, that so I cannot reduce any further. And this state 3 says that yes, there is a possibility that this item says that you have come to the end of the handle and therefore you should be able to reduce. So I will go for reduction because I cannot shift. And there is one item which tells me that you can go for reduction, right? Since I have nothing else to do, I am saying that okay, let me try by reducing. So let me go to the next slide and find out what I can do. Yes, so I can reduce using this item. So again, how many symbols to the right hand side? 2. How many to pop? 4. So when I pop 4, I have 0, 3B, 1A are all popped out. Then what I have to push in? This C. So I push this C. Now what is my next state? Next state will be determined by where can I go from the state I0 using the symbol capital C. Let us see where you can go. Yes, it is very good that we can actually make a transition from I0 to some state using the symbol capital C. The moment we do that, I see that I come to state number 4. So 4 is my current state. Again, 4 is my current state and dollar is at the input. So I know that nothing can be shifted from the input to the the stack. So let us see what is there in 4. Yes, 4 also has a very interesting thing. 4 has only one item and which says reduce. So I have no problem or no option, in fact, to do anything other than a reduction. So if I reduce that, so that is what is my next step. And so I say that then let me reduce it. When I reduce it, I see that at the stack top S comes. At the stack top S comes and just under this 0. What does that mean? That means that I have reached S from the given string, from the given sentence AAB, and therefore it simply means that the sentence is parsed. We'll find out if a little better mechanism exists. In fact, a little better mechanism exists to declare the end of an acceptance state. and we'll talk about that a bit later. But for the time being, since it is 0 and capital S, that means the initial state of the stack, and the start symbol is in and nothing else is there in the stack, then I understand that basically my and the dollar is there at the, so there are three many things. One is the stack contains nothing but the dollar, 0 and capital S, and the input contains nothing but the dollar. So input is exhausted and we have got the start symbol at the very top of the stack and the bottom of the stack, because the first symbol in the stack is nothing but the S. 0 is after all a state number. So what does the stack contain? The stack contains the state numbers and the terminals or the non-terminals. What does the input contain? The sentence and the terminal symbols only. Only the terminal symbols. What are the actions that I took? Sometimes we shifted the input symbol to the stack, and the moment I did a shifting to the input symbol, shifting the input symbol to the stack, I also found out which state transition in the DFA tells me to do that, and what is the target state, that number is also pushed into the stack. If it is a reduction step, then lots of things. First, reduction means you are replacing the right hand side by left hand side. So how many symbols in the right hand side? N symbols. How many symbols we popped out? 2n symbols, because with every symbol you have a state number. So for every symbol, 2 symbols are there. If n symbols are to be popped out, then n grammar symbols are to be popped out. Grammar symbols are terminals and non-terminals. If n grammar symbols are to be popped out, then 2n stack symbols are to be popped out, because there are n grammar symbols as well as n state numbers. So I pop out. So reduction means number 1, pop out 2n number of grammar symbols. Number 2, push the non-terminal to the left of that particular item that you use to reduce into the stack. Right? Now your stack top contains only a non-terminal which it cannot contain. So what do? I go to the previous content in the stack, right, and use that as the current state, and this capital that non-terminal as the transition element. Look at the DFA and find out to which state should I be in. So in that case, that state number will come in on the stack as the current state in which you are in. So these are the things that are most relevant and most important parameters in this whole process. So let us see how can we a bit formalize on that. Now, if I look at the SLR parser, there are a few standard components, and the standard components are: I have a stack, and I have an input symbol ending with a dollar. Similarly, I have a stack. At the very bottom, there is a dollar. Then state number is there, grammar symbol is there. State number is there, grammar symbol is there. State number, grammar symbol is there, state number is there. So at the very end, very at the very beginning, a state number 0 is there, and at the very top, the current state number is there, right? So and my driver does not look at the stack really. It only looks at the top of the stack. And what is there in the top of the stack? The top of the stack contains a state number, and it also looks at the current input symbol. So all the input symbols which are shifted into the stack are not of interest. The current input symbol, which I actually depicted by underlining the input symbol, that is of concern. So I have two elements here: current state, which is at the stack top, and the current input symbol. So using the current state and the current input symbol, I go to the deterministic finite automata, the diagram, and find out what should I do. So I find out what should I do means my action I find out. Actions could be shift, reduce, accept, error. So we have already seen shift, reduce, accept. Everything else should have been an error. When you do any one of them, you actually make in that with a go to statement as well, right? And this this DFA, the whole of DFA, can be constructed by an SLR0 method, by an SLR method, by an SLR1 method, by an LALR1 method. What was the method that we employed? We employed the method SLR0 method. That is the first method that we are trying to learn. Next we'll be learning SLR, then we'll be learning LR1, and the last we'll be learning LR1. But the whole concept is, the foundation of the whole concept is basically the LR0 set of states construction algorithm and this parser driver algorithm. And what was the driver all about? The driver was that I was narrating. Driver always looked at the configuration of the parser. What is the configuration of the parser? Configuration of the parser is read the stack from the bottom to top and read the input symbol from the current input symbol to the right. So take them together, concatenate them together. That is the current configuration of the parser. And using that configuration, what are the two primary elements that you are looking at? You are looking at the top of the stack and the current input symbol. And then you are going back to the diagram and finding out what to do. The diagram tells you whether you should reduce. If the dot is at the very end, you have to reduce. If the dot precedes some symbol, you have to shift. Now, as I said, in our example, it was very obvious which one to do, because either we had only one item which says me to reduce, or I have many elements but the dot does not precede an input symbol which occurs at the input, and therefore there was no option to shift. I had to reduce. But in certain cases it is very difficult to find out whether I should shift or whether I should reduce, and therefore in those cases the DFA needs to be modified in a better method. Maybe the DFA needs to be modified using LR1 method or LALR1 method. So we'll talk about that at due time next in some later classes. So that is all that we have talked about now, and let me go to the next slide then. As I said, that the configuration of the LR parser, that is the state of the LR parser, is the stack content and the remaining part of the input symbol. Whatever has been consumed is no longer there. Only the remaining part of the from the current symbol to the end. That is the, so this stack and input connected together, concatenated together is the state. And we are looking at SM and AI, nothing else. We are not looking at all these things. We are looking at SM and AI. And if SM and AI is available in the diagram, then what I do is shift S, and shift S means shift S to the stack, then push AI, and then push S. S means the if from using the state SM, using the state symbol AI, I jump to the state S. So I push two elements here, AI and S, right? So an example I'm narrating you, you see that I have 0A5, I'm here and it says me to reduce. So the moment it says me to reduce, I will write something like this. I'll write something like this. I reduce. Even this one also I reduce. It says me to reduce. What I do, I reduce 4 symbols I pop out and 1 symbol I push in. And from, how do I get this one? I get this one because sorry, I get this one because I know from the state number I0 using capital A, I reach state number I1, which is 1. So that I have already shown you while running my algorithm. So that is one. That is the reduction, and of course this is the yeah. So this was the shifting, and this was the reduction step that I wanted to show you. You see, it is written that if you are reducing using A producing beta dot, and number of symbols in beta dot, cardinality of beta dot is smaller, then pop 2 symbols. Remember, always I said, if the right hand side contains 3 symbols, pop 6. If the right hand side contains 2 symbols, pop 4. Again, do not count the dot inside the number of symbols in the right hand side. Dot just tells whether to shift or to reduce. Dot never tells whether you need to shift or reduce. Whether you need to push them into the, dots are never pushed into the stack or popped out from the stack, therefore. So let me tell you one more thing. I told you that the final acceptance was a bit clumsy. I told a lot of things, like for example, um, if the stack content is dollar and zero and capital S, and if the the input symbol is exhausted and input string just contains a dollar, then we say accept. So it's a bit clumsy. Instead of that, what we can do, we can augment the grammar a bit. What is meant by augmenting the grammar? You can see that the original grammar was like this and the start symbol was capital S. You must be knowing that there is only one start symbol in the context free grammar. A context free grammar, for that matter any grammar, cannot have two start symbols. So I introduce a new start symbol named a dash, name is dash, and introduce a new production called S dash produces S, and therefore my I0 contains a new item saying S dash produces dot S. So you see, it does not disturb the remaining part of the DFA. No way. Only I have one more transition here, which is from I0 on S. Where can you go? And you can go to only one state, a new state containing only one item, where S dash produces S dot. Now, what we do is, if the stack top contains, you know, uh, if the stack top contains zero, and I mean, so I can find out a very good marker for that. I'm telling you what it is. You see, so at if the, with the stack top and with the AI, if I see it's accept, then I stop. And as I said, if I find out that I cannot make a transition, the diagram does not allow me to make a transition, then we say that it's an error. Now, of course, referring to a diagram is not a very clean affair for an algorithm. So what we like to have is, we like to change the diagram into a table, right? Because that makes us working in an algorithmic manner very simple, very manageable, very plain. So the entire state machinery that I had already, that I used throughout my narration of the driver, we let us change that and let us convert that diagram into a table, because it's a state machine, and deterministic finite automata can be described as a diagram, can also be described as a state transition table. So let us try to understand the state transition table that we can have. Before that, let us look at the shift reduce conflicts that I was talking to you. You see that, let's look at this particular state which has been highlighted by some colors. You see that here, I mean, I talked about it a bit earlier, that this item says reduce while this item says shift. Now this is called a shift reduce conflict. The way we mitigated this is that since the input symbol does not contain an A, therefore it is better for me to go for reduction, because primarily I do not have any option. It is not because that I have a clear understanding of what I need to do, but because I do not have an option, I cannot shift, and then one item helps me in terms of reduction, so let me do the reduction. But this is not the way to do. We'll talk about it. It is called a shift reduce conflict. Sometimes there are reduce conflict. In one state, one string could be capital X arrow, capital X produces beta dot, another could say capital Y produces alpha dot. In the same state, these two items could be there, and that will give rise to reduce conflicts. So if you have this, then that is a limitation of the SLR parsing method. That means maybe the grammar is ambiguous, but even if the grammar is unambiguous, this may happen. Now, how to resolve them? We have some mechanisms, but there is no algorithm for that. Only a proven technique is try to change the grammar, not change the language. Language remains the same, but change the grammar and find out whether you have a conflict-free deterministic finite automaton. I mean finite automaton. Conflict-free finite automaton will deterministic finite automaton will be useful for parsing in this manner. Also, let me tell you a very thing. I mean very simple thing, very bluntly. Any context-free grammar cannot be parsed using any LR parser, be it LR0, be it LR1, be it LR9, be it LR15. There are context-free grammars which cannot be parsed using LR methods at all. So all languages that are generated by all LR methods are actually a subset of all context-free languages. So LR languages form a subset of context-free languages. Any context-free language cannot have an equivalent LR grammar for whatever LR it is. It could be LR0, it could be LRK for any K. So, right? So do not have, but the interesting story is just by LR1, it is possible to generate a conflict-free LR1 grammar. So LR1 is sufficiently powerful to for us to be able to parse even programming languages grammars. So our programming languages can be parsed using LR1. In fact, it is not parsed using LR1. It may be parsed using LALR1. Having said that, we have almost come to the end of this. Now look at this. Just see. I mean, so this is a, I mean, the grammar you can see. C dash produces C. I mean, basically, there are two rules, small rules. C produces AB and A produces small a. So it is not complete. Even maybe I think B produces small a. So this is the grammar. It is an augmented grammar. You can see this production rule number 1 was not needed because from 2, 3, 4 it is good and the start symbol is capital C. But I said that you augment the grammar, and therefore I augmented the grammar. I incorporated a new start symbol and just added one production rule so that the new start symbol produces the current start symbol. That's all I did, and then I generated the set of states. Somebody was asking me in the class that in the examination, if I'm asked to find out states, all sets of states, all states, then how big will be the grammar? The grammar will be similar to this, a very standard small grammar in which I can see whether you understand it or not. So you see here only I have 6 states for this grammar, and this is the DFA for it. Now you see that what could be the symbols? The symbols could be at the input. The symbol could be small a and dollar, right? Then why this CAB? Because in the reduction steps, at some point of time, you'll find out you are in your previous state was 0 and your current input symbol is capital A. Where do you go? Remember these situations? If not, let me take you back there. Yes, we thought that we'll be reducing using 4 symbols. I mean 2 symbols, popped out 4 symbols. 1, 2, 3, 4. Pushed C in. Now so you see, while the input does not contain any non-terminal, but I need to go from 0 using C to some place, and that is already there in my deterministic finite automaton diagram. So that I need to actually just capture in my table. So I captured them in my table in this fashion. In this fashion, for all shift operations, this part is enough. This part of the table is enough. But at certain points of time when these reductions will be there, then after these reductions I may have in a 0 and a capital C. Then where do I go? I go to state number 1. If I am in state 0, previous state is 0 and my current state is 2, where do I go? I go to state number 2. If my current state was 2 and I get a capital B at the stack top, then where should I go? I should go to state number 4. I can easily see that from I2. If I do a go to B, then I mean I take this B, this dot beyond this B, and I go to state I4. You see, from I2 to I4 on seeing the terminal and non-terminal capital B. So therefore so if you want to completely capture the deterministic finite automaton, then what you need to have here are the input symbols as well as the terminal symbols as well as the non-terminal symbols. So we divided the terminal symbols in one batch and non-terminal symbols in the other batch. Why? Because for the terminal symbols, the actions are shift the input symbol to the stack and then go to 3. Shift the input symbol to the stack. If your current state is 2 and you see that your current input symbol is small a, then you shift that input symbol to the stack and go to state number 5. Right? So S5 means shift the input symbol and then go to the state number. Sn means shift the input symbol and go to the state number L. And reduce to means these grammar rules are numbered. So reduce using the rule number 2. R4 means reduce using the rule number 4. R3 means reduce using the rule number 1. And as I said, reduction has 3 steps: popping out, pushing the non-terminal, and pushing the state number. To find out the state number, you need to go to the part to this part of the table. Um, I hope that, I mean, once we are done, then actually we have come to the end of our understanding of error parser. In the next class, it will be a formal class. It will not be so interesting, so intuitive, because we have talked about all these things. We'll just formalize them. We'll just formalize them in terms of algorithms, and therefore, so as I always said, that after all, this construction of states, this driver, none of them are to be done manually. We are doing it manually to understand it. I mean, if I have to write a sorting algorithm, then I have to take 6-7 numbers and I have to sort them manually, so that I understand how they can be sorted. Once I know what is the mechanism, what is the mechanical way by which I can sort them, then I can go to write the algorithm. Similarly here, I played with examples. Then after I played with examples, I figure out a mechanism which is quite mechanical, and then I go using the data structure that I defined: a stack I defined, an input symbol I defined, a driver I defined. Then I write the code of the driver. I understand, consult the stack top, consult the current input symbol, and consult this table. If this table takes you to a blank space, then it is an error. If otherwise, if it takes you to a non-blank state, it tells you whether to shift. If it is shift, where you go next, it is written there. If it is reduction, which rule you need to use, it says that. And after doing that, your previous state and the current non-terminal at the top will guide you to find out the next state, or which will become in the next step the current state, right? So it is, if you think about it, if you reflect on it a bit, do it, man. In fact, you must know that this example that I use now, it is not given in a book. I just created it. I created it from a small example in a book. I created this example, and then I ran through an example. So while you see that this is printed, it doesn't mean that it was like that. Therefore, there's a certain. I mean, there is a small mistake in writing 5 or 7. So the more you do this, the more you do this, the more beneficial for you to understand it. And if you once understand it, I'm very sure that you will never forget it. Now this is something that I did not do for you. You need to do I'll find out all states, and as I promised you, the number of states are not humongous. The number of states are just 12, in fact 13, because this does not have augmented grammar. I mean, an augmented grammar is necessary. So once you do that, you will get that. So my last slide is a thank you slide, but it is not a thank you slide. I urge you I urge you to take small grammars from the internet, and not find out, I mean, do the entire procedure manually so that you understand the procedure. Also, once the table is constructed, take some grammars which, I mean, I can give also, take some grammars which does not have more than 10 states, right? So that you can manage that. And so first construct the parsing table, and the driver's algorithm. Then take small sentences and run your driver using the table manually to find out that the string is correctly parsed. If you do this for 10-15 examples, you will never forget it, as I have never forgotten it, right? So thank you very much for your listening. I hope that you have enjoyed this class. We'll meet again with the next class, in the next class, with a new chapter, with not a chapter, with a new section of the same SLR parser, but that will become an SLR parser. We'll talk about an SLR parser, which is a minor variant of this LR0 parsing technique that we have just described. Thank you very much again.